Starting a new chapter today, and as you can tell, the title of today's lesson is on functions and continuity. And there are two main takeaways from today's lesson, my lesson objectives. By the time we're finished going over this lesson and you've had a chance to practice, I want you to be able to determine whether or not a function is considered to be a one-to-one function, an on-to function, or it could be possibly both. And hopefully you will be able to determine that based on a set of ordered pairs that are given to you, a mapping diagram, or a graph. You should be able to tell by looking at any of those three examples of functions. And then finally, number two, we want to know whether or not a function is discrete or continuous, and we'll be able to understand what that means in the second half of our lesson. So first of all, we're talking a lot about functions. We need to make sure we remember what a basic definition of a function is. And here it is. It's a relation. And if you're wondering, well, what's a relation? You may have recalled from your past math experience, this is just a set of ordered pairs. A set of ordered pairs. Okay, so we have a set of ordered pairs where each element of what we call the domain, and we're going to talk more about what that refers to on the next slide. Each element of the domain is paired with exactly one element of the range. Okay, so in defining function, we threw some other terms at you that we need to make sure you understand. So let's just do a quick little terms review. And what I've done here is I've just picked an ordered pair at random. And for this -2 in the ordered pair, we have really four different ways of characterizing or describing what this -2 actually means, or what does it refer to in this ordered pair. And that same thing holds true for the 7. There's four different ways of describing the 7 that's sitting in this ordered pair. And those choices are provided for you on the outskirts here of my slide. So this should be pretty easy. One way of describing -2 is by saying that it's the x coordinate of the ordered pair, and so therefore the 7 would be considered the y coordinate. That should be pretty straightforward. Okay, we could also think of the -2, the x coordinate, as a member of the domain. Okay, keep that in mind. So we associate the x coordinate of an ordered pair as being part of a domain. The y coordinate of the ordered pair then would be considered part of a range. Okay, we've taken care of those. We also think of the -2, the x coordinate, the domain. Another way of describing that is by saying that these are input values into a function, and they produce a resulting output. Okay, so we connect the x coordinate, the domain, and the word input. Those are all basically synonymous. They work together. And y, range, output, those are all along the same lines. And then finally, this -2 represents an independent value, or maybe you've heard the term independent variable when referring to an equation for a line. For example, here's a different equation, linear equation. And if I wanted to come up with a table of values in order to just see what points actually fall on this particular line, then I have choices. I can pick any number I want to plug in for x in this equation. And if I do pick a number, say 2, then I plug that in. -2 times 2 is -4, and -4 plus 3 is -1. Well, I got to pick any number I wanted. That's why the x variable in this case is called the independent variable. The -2 in my case here, it's a value. It's called the independent value. And the 7, or in this case over here, the -1, depended on what I picked for x. And so the independent value corresponds with the x coordinate, and the dependent value corresponds with the y. Okay, and hopefully you can see that. I got -1 because I plugged in 2. So y is going to depend on what I plug in for x. All right. So I hope that kind of helps you maybe refresh your memory a little bit on some terminology, because especially in this lesson we're going to be dealing with terms domain and range, so you need to be connecting domain with the x coordinates of an ordered pair, range with the y, and then when we start evaluating functions, the input, we're going to be inputting a number in for x and then doing some math to get a resulting output number, which we're going to call y in this ordered pair. Alright, so with that said, let's see if you remember how to determine whether or not a particular set of ordered pairs, that's what a relation is, can you tell just by looking whether or not a relation is a function? Well, I gave you a definition, but it's also important for you to be able to determine just by looking at the set. And the most basic, the most fundamental way of determining whether or not a relation is a function is pay attention to the members of the domain. Okay, remember that means the x coordinates of each of these ordered pairs. My domain here would be the set 5, -7, 0, 3. I don't have any numbers that repeat themselves in the domain. Therefore, this would be considered a function. So it's pretty simple. If you're looking at a set of ordered pairs, look at the domain and see if you have any repeat elements or numbers in the domain. And if you don't, then you have a function. A letter B is just another way of looking at a relation. This is called a mapping diagram. So we have members of the domain that are paired, or we use the technical word mapped, to a particular range number, but the same idea is true. Do you have any domain numbers that are basically used twice, or in other words, they're mapped to two different range numbers? Well, 6 maps to 8, 4 maps to 10, 9 maps to 10, -2 maps to 14. And maybe you're thinking, well, I see a range number that has to be used twice. It's paired up with both 4 and 9, but that's not the issue. To determine whether or not a relation is a function, we need to know, does a domain number map a particular single domain map to 2 or more range numbers? And the answer here is no, they do not. We have no domain numbers that are actually being used twice. If we were to show this in ordered pair form, like we did in letter A, it would look like this: 6, 8, 4, 10, 9, 10, -2, 14. Well, you can see here pretty obviously that there are no repeats in my set called the domain. So my bottom line answer here is yes, this is also a function. Okay, let's look at letter C. Let's look at the domain. -6, 2, 3, 2. Do you see it? I've got the number 2 that shows up twice. Therefore, this, letter C, cannot be a function. No repeats in the domain. Letter D, another mapping diagram. And here's a big clue when you're looking at a mapping diagram. Look for a particular domain number, like 8, that has 2 or more arrows branching out from it. You see that? So in other words, if we were listing ordered pairs, we would have 8 mapped to 6, and we'd also have 8 mapped to 12. Well, this indicates a repeat in the domain, so therefore this cannot be a function. And then letter E, just another way of showing a relation. This is in graph form. There's two ways of looking at this. If you notice, we've got domain -4, -2, 0, 4, and 4 again. So if we were listing the domain, we would have to show that really we have the number 4 that's used twice in the domain, and that's a no-no for functions. But you also might have remembered from Algebra 1 or pre-algebra, we had this thing called the vertical line test that's helpful. And the vertical line test says if you can draw a vertical line and touch two or more points on a graph, then that proves that that is not the graph of a function. And so we basically prove this in two different ways. We have a repeat domain member, which is the number 4, and this also does not pass the vertical line test. So I've given you some review of how to determine whether or not a relation is a function. Well, now let's go one step further. If a relation is a function, then we need to be able to classify them in really one of three ways. Is this function a one-to-one? Is it called an onto? Or it could possibly be both of these, a one-to-one and onto. And part of your homework assignment will be your ability to recognize functions in one of these three ways. If it's not a function, obviously, then it's not any of these. So let's just take a quick look. I've given you definition, and then this colored statement is just another way of saying it. If you don't understand the mathematical definition, maybe this is a different way of approaching it that might make more sense. And then here's a picture. Basically, here's the one-to-one. Every element of the domain pairs up to exactly one unique element of the range. And this is key. The blue statement is key for one-to-one. You cannot have any repeat y values. Okay, we've already established that we can't have any repeats in the x because that makes it not a function. We're talking about, in classifying here, all of these are going to be functions, so it's up to us just to determine, okay, well, what kind of function? All right, so obviously there can't be any repeats in the domain, but if you want to know whether or not a function is one-to-one, then you can't have any repeats in the range. All right, so do you see how 1 is mapped to D, 2 is mapped to B, 3 is mapped to A, and so that would be considered a one-to-one, one domain matched up with one unique range. That makes sense. Kind of the name gives it away. One domain to one range, period. Well, let's take a look at this onto function, and then we'll go back and see why is this first mapping diagram not onto. Well, here's the big deal about an onto function. Here's the definition. Every element of the range also corresponds to an element in the domain. But to me, this is an easy way to remember onto. If every single potential range element or number in the every item in the range is accounted for. Okay, so in other words, look at your range and make sure that it has a partner in the domain. Okay, and again, it doesn't matter here that C goes to 3 and to 4. This is going to be a function because we don't have any repeats in the domain. But what makes it onto is that every item in the range has been accounted for. It has a partner in the domain. Okay, that's why this first example is not onto. Do you see that? We have a potential range element here, C, that is not being used. It has not been accounted for. All right, so although it is one-to-one because we have one domain paired up with a unique range, not every element in the range was used, therefore it cannot be onto. Okay, and the reason why this cannot be one-to-one here is because we have a repeat in the y's. All right, so that's kind of a contrasting example here. Why this is onto and not one-to-one, we have a repeat y, and why this is one-to-one and not onto, because we didn't use this potential range element. Well, what happens when they're both? When they're considered to be both one-to-one and onto, then it's really a combination of these two. We have unique domain paired up with unique range, as you can see here, and then all of my range values have been used. So it's really like going both directions. We have uniqueness. We have a one-to-one going in both directions. Okay, it's one-to-one going from left to right, and that's also true going from right to left. Okay, so every map, I just described it this way in green, every x maps to a unique y, and every y maps to a unique x. It's really unique pairings going in both directions, from x to y and from y to x. Okay, so with that said, we'll get to some homework examples. A lot of things to do here. First of all, state the domain and range of each relation. Alright, so remember domain, we're going to say it like this, domain D, and we'll use the curly braces for set notation. And domain will be these x values, 4, 7, -5. Range will be the numbers that are being mapped onto 6, 1, and 0. Alright, that takes care of state the domain and range. Determine whether each relation is a function. Well, do we have any repeats in the domain? We do not, so I'm going to say function. Okay. If it is a function, is it one-to-one, onto, both, or neither? Basically, it's going to be neither if it's not a function. So let's see, do we have a unique pairing, domain to range, domain to range, domain to range? And yes, that's true. It's also true going the opposite direction. So this would actually be both. This would be considered one-to-one and onto. So we're going to just say it's both. Alright, and that finishes off my answer for letter A. Alright, so let's try letter B. This is given a little differently. It's a table of values, but it's the same idea. Let's determine whether or not this relation is a function. We'll look at the domain. Do you see any repeats? And I do not. So we're going to say it is a function. Okay, if it is, which it is it one-to-one, onto, both? It can't be neither because it is a function. So let's see, do we have pairings? I've got -3 mapped to -5, 7 maps to 2, 4 to -8, 9 to 4, 11 to 2. Okay, alright, so I don't have repeats in the domain, but I've got repeats in the range. And if you go back, remember, in order for it to be one-to-one, we cannot have any y values repeated. So we're going to classify this as onto. Every y has been used, and it can't be one-to-one because we have repeats in the range. Alright, so I didn't state domain and range, so don't forget that. So let's go do that real fast. Domain, -3, 7, 4, 9, 11, and then range, squeeze it in right here, -5, 2, -8, 4, and then I don't like to show these as being used more than once in the set, so you don't have to show these repeats more than once. So I just show the ranges -5, 2, -8, and 4, and that's my complete answer. Alright, so letter C, just another way of showing a relation. Here's a set of ordered pairs. First of all is, well, let's do the domain and range before I forget again. So let's pick out all the x coordinates. We have -5. We have -5 again, so that should tell us something. -1, 0, and 2. Notice I just did those in order from left to right. And then the range, -1, 2, -1, 2, 5, -2, and then I got 2 again, so I'm not going to list it more than once. So I'll make sure I got them all. -1, 2, 5, -2, and then +2. So there's two ways of knowing that this cannot be a function. It doesn't pass the vertical line test, and also we have repeats in the domain. So I'm going to say not a function. And if it's not a function, then there's no need to try to classify it, of course. Okay, so here we are with letter D. What's the domain? 8, 16, negative 24. And the range 3, 6, 9, 12. Well, this cannot be a function because I've got a domain element that's really paired up with two different range elements. Remember how you can tell in a mapping diagram, if you have one single number in the domain that has two arrows branching out from it, it cannot represent a function. Okay, so that's the kind of thing you'll be doing on 14 through 16. All right, so let's take a look at some examples on 17, 19, and 22. We're going to graph each equation, determine the domain and range. All right, so let's just go ahead and work on that part first. This is just a linear equation. We're familiar with how to graph these, of course. We start with 3 as a y-intercept and then count a slope of negative 2. All right, and then you'll want your straight edge. And I'll make sure this is going to be a solid, and it is. Okay, so we'll connect our dots, and there's the line y equals negative 2x plus 3. All right, now determine the domain and range. All right, so when you're looking at a graph, you're thinking domain, again, that's the x coordinates of all the points that would be contained on this line. Well, do you realize that this line really goes forever and ever in both directions, all the way to the left forever, and it will continue to go all the way to the right forever. So the way we describe the domain, all the x values that would be ordered pairs on this particular line, it would be all real numbers. Every real number we could think of for positive and negative infinity, because that's the way it's going to continue to go, both left and right. Okay, so for range, now you're thinking up and down. Will it continue to go up forever, and will it continue to go down forever? And the answer is yes, it will in both cases. So not only will every single real number be involved in the x coordinates on this line, it will also involve every single real number as y coordinates. So we'll describe the range in the same way. It's going to be all real numbers. It's going to go forever and ever, left and right and up down. Okay, so we've taken care of the domain and range. Now, is the equation a function? Yes, it is, because the vertical line test, for one thing, if I draw a vertical line anywhere on this graph, I'm only going to touch one point. So another way of saying it is my domain will never contain any repeats. So that also would prove that it's a function. Is it one-to-one, on-to, both, or neither? Well, if it's one-to-one, then I don't have any repeat y's, and that's going to be true. If it's on-to, every single potential y should be involved, should be used. That's also true. And so this is going to be both one-to-one and on-to. And now we're going to get to this new term, these new terms. Is this discrete or continuous? Well, you can probably tell just by looking. Continuous means it goes forever and ever and ever without a break in the line. And we'll take a look at what does it mean to be discrete, so you can get an example. If I can spell continuous. Okay, so there's the complete answer. Draw the graph, identify the domain and range. Is it a function? What kind of function? And then classify it as discrete or continuous. Let me just throw you a real quick example of what does it mean to be Well, this would be a good example of discrete. There are obviously some values for x that are not involved in this graph. If it's just three ordered pairs that are not connected, then this could not be a domain of all real numbers, and it couldn't be a range of all real numbers. This would be a good example of a discrete function. It is a function because it passes the vertical line test, but it's not continuous, moving continuously, containing all points forever and ever, going in both directions. All right, so let me put my line back and we'll move on. Okay, let's take a look at y equals 4x squared. What does this graph look like? Well, let me give you a clue here. Whenever you see squared, that means quadratic. And the word quadratic can be spelled really funny, and this will maybe help you remember what the graphs look like. Okay, I always spell the word quadratic with a giant U because that's what they produce. They either produce U-shapes opening upward or upside down U's, obviously opening downward. But literally the word quadratic means, in case you're wondering, squared. So anytime you see x squared or whatever variable, it may not be x, but something squared in your function, then it's got to be a quadratic, and it's got to produce this U shape, either upright or upside down. So might want to do some this little table of values for this one. It's easy enough to put in, for example, 0 for x, and if I do, I get 0 for y. Maybe let x be 1 and I get y is 4. Okay, and well, if it's got to produce a U shape, you probably can see that I'm going to get the same value for y if I let x be -1, because if I input -1 here and square it, remember PEMDAS says you square then multiply. -1 squared is 1, and then 1 times 4 is 4. So I got the same result as an output for this both 1 and -1. Okay, well, that tells us something. It is a function, but it can't be one-to-one, right? Because I'd have to have unique. I can't have any repeats in the y's in order for it to be one-to-one. So oh, that's probably good enough, because if I go to 2, then I'm going to be up at 16, and that's going to be beyond what your graph paper will be able to handle. But I'll just go ahead and estimate 2, 16, and you also get that for -2. Okay, and if you're not sure how I got that, I just input 2, square it, that's 4, 4 times 4 is 16. So then with smooth curves, it shouldn't be a V shape, it should be a U shape, and it's kind of ugly, but I think you get the picture. Alright, so once again, our directions are graph. We did that. Determine the domain and range. Okay, so let's do that. The domain, again, you're thinking horizontally. What numbers are available to be used, can be used to produce this U shape that's going to go, it's going to keep going forever and ever. It's just going to keep getting wider and wider as the numbers for x get bigger this way, and it's also going to continue to get wider as the numbers for x get bigger this way. So basically we have the same situation as we had before. The domain is going to be all real numbers. Okay, but let's take a look at the range. Again, thinking this way, do you involve every single real number in this graph when it comes to the y coordinates? Well, obviously you don't, because none of these negative numbers are involved in this graph. It's only the numbers from 0 and upward. So we can't say all real numbers because these are not involved. So the way we're going to state the range is we're going to say for, we can say y greater than or equal to 0. Any y, again, y stands for range, greater than or equal, because 0 is part of the range, and then from there it's just all the positives for y. Alright, so we've taken care of domain and range. Alright, is the equation of function. Sorry, I went back wrong way. Is it a function? Yes. It passes the vertical line test, and there are no repeats. There will not be any repeats in the domain. So now let's get specific. Okay, well, what kind of function? Is it one-to-one? Well, we've already said that it can't be one-to-one because there are repeats in the y. And here's another way to test one-to-one. You know about the vertical line test, but there's also a horizontal line test. And the horizontal line test says if I can draw a horizontal line and touch more than one point on the graph, then that's testing whether or not it's one-to-one, and in this case it can't be. Okay, but it is on 2. Okay. So you can see that it is on 2 because again, all the potential y values for this function are being used. And then the last thing to do is to determine whether it's discrete or continuous. Well, again, if you have this curve that designates that it's going forever and ever, then you don't have any breaks in a line. You don't have separate ordered pairs that are not connected. That would be an example of discrete, but in this case all of the ordered pairs are connected with this smooth curve that indicates going forever and ever upward. Then our final answer here would have to be that this is continuous. Alright, so let's take a look at one more. This is a cubic function, and probably the easiest thing to do here is to, once again, to think about a table of values and pick some easy numbers that you can plug in, starting with 0. I think that's always the best place to start. Start with small numbers. And if you input 0 here and simplify, of course 0 cubed is still 0, 0 times negative 2 is still 0, and then 0 minus 1 is negative 1. So there's a point on my graph, 0, negative 1. Remember, we're just doing inputs in order to determine the related output. So let's try another easy number. What about positive 1? Negative 2 times 1 cubed minus 1. So remember, PEMDAS says you do the exponent first. 1 cubed is 1. 1 times negative 2 is negative 2. And then you do negative 2 minus 1, and that's negative 3. So I get the point 1, negative 3. Let's try positive 2. Okay, and same type of deal here. 2 cubed minus 1. 2 cubed is 8. 8 times negative 2 is negative 16. And negative 16 minus 1 is negative 17. So for positive 2, I'm way down here. Okay, and I'm just going to show it. I'm not going to change my units. Well, now let's try some numbers going the other direction, like negative 1. Okay, so negative 2 times negative 1 cubed minus 1. So negative 1 cubed is negative 1. And negative 2 times negative 1 is positive 2. And then you do positive 2 minus 1, and you get positive 1. So there's an ordered pair on this line, or curve, negative 1, 1. So you can kind of see it taking shape a little bit. So let's try one more, negative 2. Alright, negative 2 is an input into this function. Negative 2 cubed is negative 8, and negative 8 times negative 2 is 16, and 16 minus 1 would be 15. Okay, So again, let me erase some of my work up here. And I'm just going to estimate, here's -2 and then 15 way up here. So this is a typical cubic function. They will take this kind of shape, especially if the lead number is negative. They do this kind of thing. It's almost like a real skinny backwards S shape. If this number were positive, then it would be doing the other way, like that. Okay, so that's pretty close to the graph of this. So we've sketched the graph, determined the domain and range. All right, so again, so for domain, you're thinking horizontally, and just think about how this graph is going to go forever and ever. It's just going to keep getting wider and wider and wider. I know we can only see a snapshot of it, but it's going to continue on broadening out as the numbers for x keep increasing. It's just going to keep getting bigger going up or bigger going down. So basically, we're going to characterize the domain as all real numbers. All right, and so now let's think about the range, and now you're thinking about the y's. Well, what y coordinates are going to be involved for all of the points that you can think of on this graph? It's going to go forever up and it's going to go forever down. So once again, the range is going to be all real numbers. Okay, so we've graphed it. We've stated the domain and range. Is it a function? Yes, it passes the vertical line test. It is a function. So now let's see, is it one-to-one, on-to, or both? Well, there are no repeat y values, so it's one-to-one, and every single potential y value is used, so it's on-to, and so therefore we would just consider it to be both, one-to-one and on-to. And let's see, is it discrete or continuous? Well, once again, it's a smooth curve. There are no breaks in this curve, so we would say that it's continuous. Okay, so finally, last example, and this should be more of an Algebra 1 review. If you're given functions, and this is just another way of giving you the input for a function, it's going to be your job to determine the output. So let's just take a look at this letter A. This says f of -7. So what I'm going to do is pick the f function, and in place of x, just like we've done here, in place of x in this function, I'm going to put -7. So this is like we did with function cornhole. This was the number on the beanbag, and now we take that number and we plug it in, we input it, and see what comes out as the output. So this would be -21 plus 2, and -21 plus 2 would be -19. Okay, now you don't have to do this, but I hope you understand that what you just done is, for this linear equation, you've just found an ordered pair. That's a point that falls on that line, but we'll do that more later on. Okay, so my answer for letter A would be -19. So now letter B says evaluate g of -2. Okay, so we're going this time to the g function, and we're going to put -2 in for x. And this is where you have to be careful. Remember PEMDAS, you do the squaring first. -2 squared is +4, and then you do the multiplication. So the answer for letter B is -8. And then finally, this letter C is evaluate h of 3/4. So this one's a little more complicated, I guess, because we got to deal with this fraction. So it's the same idea. We're going to take 3/4 and we're going to put it into the function for x. Everywhere we see x, we're going to input 3/4, and then it's going to be our job to come up with the output using PEMDAS. So once again, remember to square first, and 3/4 squared is 9/16. Okay, and then I'll come back. I'll just do this one PEMDAS step at a time. Now we are going to do the multiplication. So we could do some cross canceling here if you want to. That would become -1, and this would become 4. So we end up with -9/4. Okay, and then this would be -6/4. I'll just keep it in fourths for now, since we're going to combine these anyway. And then I've got 5, which you would think of as 20/4. Okay, so now we combine all of these together. -9 minus 16 is -15/4, and -15 plus 20 is 5/4, and that would be my final answer. Okay, so that's just evaluating functions, finding the output for a given input, and hopefully you remember that from Algebra 1. So that is this lesson. A lot to take in. Practice well, and let me know if you have any questions.